Okay. So, are you one question, right? So I hit the mute button on my laptop. Are you able to hear me through with the stream right now? Not on the phone, but on the stream. Sure. Okay. Okay. Mic test. One, two, three. Mic test. One, two, three. Hello, everyone, and welcome to today's session. Are you all able to hear me? If you can post a quick message, I can get started. Okay, great. So I wanted to start off by saying thanks to ND Prabhu and his team at SixPhrase. I think they're doing a really good job training the graduates and help shaping their future. So the webinar series is a great idea, especially during the lockdown times. And I want to thank them for having me here. And I'm really happy to talk to all of you. My name is Sriram, and I've been in the semiconductor industry for about 15 years now. I finished my bachelor's of engineering from Tamil Nadu, pursued my master's in VLSI in the US. I work for an FPGA design company called Altera as a hardware design engineer. This was in the US for about 5 years before I moved back to India. And I've been with Intel for more than 10 years now, and currently my role is an engineering manager. So when I started out, I did have a lot of questions, especially coming from an electronics background, as to what is this industry all about, and what kind of jobs exist in the industry, and how are we even supposed to get to know some of these jobs, and a lot of such questions, both when I finished my bachelor's as well as my master's. And what I'm trying to do here is I hope to answer some of these questions in today's sessions, and I hope you find it informative. I think I have material planned for about 35 or 40 minutes, and I will be running a live Q&A session after that. So if you have any questions, just write them in the chat window, and I'll try and answer them to the best of my knowledge. So with that, let's get started. So before we jump into the topic, I just wanted to take a moment to inspire you. So if we were to ask ourselves, what was the most important invention of the 20th century? What would you think? I'll give you a few moments to gather your thoughts. There have been quite a few in the 20th century, right from the invention of antibiotics, invention of automobile, inventions of television, rockets, and so many more. But there's been one invention that has fundamentally transformed the way we live our lives. The human race is far more connected and intertwined than ever before. Don't you agree? So what led to this amazing change? What kickstarted this age of information? And the answer is this innocent looking device called the transistor. This is truly a modern engineering marvel. It's simple, it's elegant, but it's been the foundation of all our modern computing. It is part of every modern device that we know, from cell phones to music systems to the amplifiers, the personal computers, our cars, our flights, televisions, our video game consoles, even our washing machines, and many more. So this invention is what helped me look up information for this very same talk that I'm giving. It's what helped me create these slides and figures. And definitely without it, I wouldn't have been able to share it live to all of you. So the real question is, what made it such an impactful innovation? How did it get to be part of so many people's day-to-day life? So the advancement and improvement of transistors over time is governed by a principle called Moore's law. I hope some of you have come across this term before. So Gordon Moore is actually one of the founding fathers of Intel, and this law was named after him fondly as the Moore's law. Moore's law is not really a law of physics, as some people might think, but it's more of a law of economics, something that started as a mere observation. Right? So it stayed as an observation for a few years before it became a guiding principle for the company. And I think a decade later, it became a mantra for the entire industry. And not to forget, this has been holding true for many decades now. So what is this Moore's law in simple words? So Gordon Moore made an observation that roughly every 2 years, the number of transistors that you can pack in a small area of integrated chip doubles. So this sounds good, right? You think, okay, why not? Twice the number of transistors every couple of years. However, amongst you, right, the people who understand the power of compounding really get this factor, right? You will immediately see just how bloody good this is. It's not just that the transistor by itself became one of the greatest inventions, but this rate of improvement in efficiency that will truly lead to this age of information. So here's a plot, that shows this data, right? So from about 1970 to a few years before 2020, it shows how the cost of a transistor has been steadily decreasing, over the years, and what that has led to is be able to pack more and more transistors on, the computing platform or the solution that is available to us over a period of time. So let's try and understand this really out of the world scaling with an example. So if you take Intel's first generation microchip, right, the 4004, which was introduced in 1971, and compare it against the latest chip that Intel has on the market today, say, for example, a Core i5 processor, you can actually see the power of Moore's law at work here. So Intel's latest chip offers performance which is 4,000 times faster, a power which is 90,000 times lesser or 90,000 times more energy efficient, and a cost that is 60,000 times lower than what it started out to be. So this is really impressive. There isn't a single industry on the earth that has provided such numbers, not even close. And just to appreciate this even better, why don't we try and take the same figures and map them to another industry? Say, for example, the automobile industry. So the same year that the 4004 microchip was introduced, there was a very famous Volkswagen car that we are all familiar with, the Beetle, was also manufactured. And if we apply the same rate of improvement that the microchips did under the Moore's law to this example, the numbers look staggering. So you should be able to drive the car today at 5 lakh kilometers an hour. That's the speed. And you should be able to get about a mileage of 10 lakh kilometers for just 1 liter of petrol. And it should cost you just 10 rupees to buy this car. So this is the amount of scaling that the microchip has gone, right? So I hope you're able to see it clearly now that the sheer scale of this efficiency improvement over time that has driven innovation and truly funneled the advancement of mankind. And the reason I wanted to spend a few minutes on this today is it's vital that we understand and appreciate these facts, since it's this very trend that became foundational to the entire semiconductor industry. Okay. So there were a couple of things that I wanted to talk to you today. So one is try and explain what does a semiconductor value chain look like, and talk about what are the steps or process that's involved in a semiconductor product lifecycle. So first, let's go over the value chain. So the semiconductor industry is a $500 billion industry, right, which contains consumer products, including televisions, laptop computers, tablet, mobile phones, to more sophisticated equipment that's used in, aerospace, business operations, industrial operations, or even national defense for that matter. So the non-stop consumer-driven demand to have more and better capabilities, features, better reliability, increased speed, requires a lot of heavy investment in research and development R&D efforts within the companies, which spans from design to low-cost manufacturing, testing, assembling the chips, packaging them, and even distribution. So this is accomplished not just by one company, right? There is a string of companies that are interconnected in a very complex setup that's able to cater to the demands of the customers. And there are so many disciplines involved And the reason we are taking interest about this today is it actually translates to a multitude of career options, and it's really useful to understand, what are these companies, what do they do, and what domains under which they operate under. So the firstly, we have the EDA companies. So the EDA stands for Electronic Design Automation. So in the last 30 years, obviously across domains, things have gone to CAD-based design, which is true for the semiconductor industry as well. So there are a lot of tools that some of us use, which could be the simulators, that we're familiar with. Like if you want to simulate a circuit using SPICE, or if you write lines of code on MATLAB, or even RTL for that matter. So all of these need simulators, and the simulators come from these EDA companies. Or of people who are familiar with schematic drawing, where they draw the transistors in layout. So even those layout editors, schematic editors, design suites, all come from EDA companies. And that's just not it. There's so many more. As you go through the product design cycle, there are many tools that help you check the integrity of the design, how the quality of the design, a lot of tools for regression, debug tools for like waveform viewers, and many, many more. So there's a slew of tools used by every semiconductor company, and a lot of them come from these EDA vendors. Some of them are developed in-house as well, but these are, I've just quoted a few examples here, like Synopsys, Cadence, Mentor Graphics. I think these are names that you should be familiar with, but they primarily concentrate on supplying the EDA tools. So the next set of companies is the IC design companies. This is where the actual hardware design is carried out. The definition of the architecture of a product. What kind of feature set should a product cater to? Should this be a desktop grade chip? Should this go on mobile phones? Should this go on laptops? Or should this go on an IoT platform? The very definition of what a particular chip should cater to, and then the actual hardware design. Validating the hardware design, and once you validate it, is to actually physically design it so that it can be fabricated into the piece of equipment that we own. So all this is carried out by the IC design companies. So this is really the bread and butter set in this value chain for semiconductor companies. Companies such as Intel, AMD, Samsung, Nvidia, and many others fall under this category. So the next set, which is often a set that's not really associated with hardware or semiconductor companies, is the actual software and embedded software set of companies. So there is a popular belief amongst us that the semiconductor industry is just for hardware engineers. That's really not true. In fact, what surprised me personally was that the number of software engineers clearly outnumber hardware engineers even at Intel. So there are a slew of software development effort, which starts from writing, drivers, writing firmware, operating system optimization, open source library development, and many, many more. So significant amount of software and embedded software development takes place at, again, Intel and Samsung, AMD. Lot of companies where hardware is manufactured, it goes without saying there's a tremendous team building software so that the users can actually tap into the true potential of the hardware that's being designed, be it compiler design, like I said, firmware design, routines, ISRs, and so on. And once the design is complete, so the next step is to make or actually fabricate the chip. So this is one area where there has been a lot of consolidation over the years. Like 30 years back, you would find every hardware company or every semiconductor company having its own fabrication unit. Not anymore. So as the technology has advanced over the years, I'm sure a lot of you are familiar with numbers like 150 nanometers, 110 nanometers, 90 nanometer chip, 65 nanometers, and so on. So this is indicating how advanced or how small the feature definition is for a particular manufacturing process. And the smaller the number, the more transistors you're able to pack, which really goes back to the Moore's law. So as technology is advanced, the amount of engineering effort, the amount of equipment that needs to be manufactured, the engineering solution around it, I think has become really complex that it's simply not feasible for a lot of the smaller companies out there to have their own fabrication units. Today, if one were to start a fabrication unit, on one of the latest technology nodes, we are talking about a multi-billion-dollar investment. So clearly, a lot of the mid-sized companies out there can't do that. So the way the industry is moving is this just handful of companies, for example, like Intel, TSMC, or Samsung, who have their fabrication units. And so many of the other companies who do design and don't have their own fabrication unit use any of these services to manufacture their own hardware. And this is where I said that there's been a lot of consolidation over years. So people with a lot of device physics background, so chemical engineers, so they are really sought after in this particular set of companies. And as I mentioned, the whole assembly line has become so complex that a lot of things have been moved to automated way of doing, which means there's a huge scope for automation engineers to expedite the whole process. So the next step is the assembly and test. So once your chip is fabricated, this is still at a very small scale. I mean, you can't really hold this even with your bare hands because you would cause some kind of an ESD event. So this needs to be packaged in a very safe way, which then looks like the chips that you and I are familiar with, right? The one that has like the small spider legs. So the assembly and test sort of companies do that. So they basically test it, package the die. They sort it to make sure that is it a fast die, is it slow, and depending if it's a fast, it might be sold as a higher performance device. If it's not up to the mark, it will be sold for a much cheaper price. So all this is done before it is sent to the OEM vendors. So they are the final set of companies in this semiconductor value chain. So these are the companies that we are definitely familiar with, the Apples, the Dell, Samsung, HP, who actually end up selling the device that we buy, be it a laptop or a phone or a tablet. But these are the companies that take the ICs and integrate it as part of their platform, and then obviously bring it to the customers. This is the semiconductor value chain. I think it's important to internalize the slew of opportunities that are available, and also to know some of the names of these companies, right? So because a lot of these companies, in fact, all these companies will have their own job portal, and it pretty much goes like jobs.intel.com or jobs.cadence.com. And if you really know the company, you can always spend some time checking out what are the relevant job opportunities to go after. Okay. So moving on. So the next topic that I had in mind was to talk about what would a typical semiconductor project cycle look like, right? So this is another question that I had. This was a burning question in my mind when I started off as a graduate. Right? So how does it go from end to end? What are the various pieces or cogs of the gear that's involved to get the final product out? So what you see here is really not something sophisticated or rocket science, but unfortunately, no book, or material kind of gives all this information in one place. And so, given that I was really looking out for this information when I started out, I put this, thinking that maybe some of you might find it useful. So the first step, or the first major step, is coming up with the product definition. Right. So this is a really important phase where there are a lot of engineers who popularly call themselves as product engineers within the companies, go and do a whole bunch of market research. Right. So we've been having X, Y, and Z products in our pipeline over the last few years. How do we make it better? What do the customers need? And sometimes this is driven by the customer need and talking to them. And sometimes the really good companies are able to predict what the customer needs ahead of time, even before the customer themselves knows about it. So there's a lot of multi-year effort that goes on in coming up with what interests or what could sell or what could be marketed. And that's what comes from the product definition team. They look at stuff like workloads. For example, if you take an FPGA, so we know that any design that we have, we can burn it on an FPGA to prototype. Right. So, but the question is, what is a sample set of designs do you consider while tuning the architecture of this FPGA? Right. So that's what's called workloads. So a lot of these product engineers are in constant touch with the OEM vendors or other companies to understand the workload. So they usually have like a dictionary of workloads that they run through their performance analysis metrics and tools to say, what, increasing the memory from, let's say, 2 MB to 4 MB is going to really help the end customers. So this is driven by data, so it's driven by workload. So a big part of product definition is to identify what are the key workloads that could represent our true customer set. And obviously, always look for key differentiators, right? So while it's good to say that you can do what you're doing faster, I think people always appreciate that. But anytime you bring in a new feature, right, and that is what brings a lot of value to the product. So, for example, when the touchscreen was first introduced, right? So that's just an example. So anytime there's a key differentiator that you introduce, I think there's a lot of product value for that. And last but not the least is the cost analysis itself, right? So there has to be a detailed study of what is the cost to introducing a feature, and this cost is not just simple manufacturing silicon cost, right? That is an important aspect too, but things like development time, right? The expenses that you don't really get back, the engineering time, the testing time, how much time goes into the software development to take care of this new feature, and so on. So across the board, there's a detailed analysis that's carried out to make sure that there is a benefit of bringing in some of these new or key features with respect to cost. So this is the first step that happens, and this step happens long before sort of the engineers get on to designing the product. And then comes the front end design. So right now the product definition team would give a very clear set of specifications saying that, we need all these features to be improved or some of these new features to be introduced. So the front end design team is the team that goes about implementing these requests, right? So you start off looking at architecture first to make sure that is my current architecture, does it scale well enough to support these new features, or do I have to rethink from the basics? So that architecture work happens, and once you get some of those high level architectures in place, you get into the actual hardware design. And this could be a custom circuit design if it's very analogish or mixed signal, or for most of the digital design, obviously we go through a hardware description language, for example, the Verilog, and code. The hardware is written as code, and that code is what then gets transformed or translated to hardware. And it's very important to keep track of the performance as you're designing your system. So that's where virtual models come into play, right? The actual hardware is going to come to your hands much later, or even simulation using the hardware models is actually really slow. I mean, if you're running huge regressions across the workloads that we saw in the earlier step, this can actually, for many of the products that we design, take months to finish, right? So simply we can't afford that kind of time. So what we do is have what we call as virtual models. These are C models or system C models, which are really fast, which mimic the hardware, that we can actually iterate a lot of simulations and workload analysis in a matter of sort of minutes or hours. And sometimes we even take the design that we have and put it on FPGA to very quickly prototype to understand is there any corner cases that we probably didn't anticipate and catch during the design. So this is where the bulk of the design time is spent. And then once the design is complete, there's a lot of emphasis on validation. In fact, among hardware itself, I think I can easily say that the validation engineers make up for most of any semiconductor hardware set of jobs. This is a team that has a lot of formal methodology and process to validate the design. So they clearly have a lot of understanding about the IPs that goes into the silicon. I mean, we are familiar with things like USB or PCI Express and some of them, or DDR for memory. So these are very, very complex IPs with a very rich set of interfaces. So the front-end team, validation team, makes sure that some of these are validated to the T. And a lot of times these components communicate with one another on another chip. So those intra-chip communication protocols have to be validated. And the communication happens using a fixed set of protocols, and there are a lot of standards for them. There's OCP and there's AMBA, APB, AHP, and many more hardware protocols that exist. And this is because when different people design their components, you still want to have a common language between the two so that they can talk to each other flawlessly without any translation errors. So some of those protocols are validated in detail by the validation team. So now once your product is defined, you go through the design phase and you validated it. And now you get into the physical design space. So this is when the code that we write or the RTL description or the circuit description that we have gets translated into something that can be manufactured on a die, on a piece of hardware. So the team, so that step is called the synthesis. The synthesis is to basically translate what's in sort of human readable form, like an RTL or a Verilog or a System C, to something that the machinery can understand and fabricate. So they have a bunch of steps like synthesis, place and route, timing convergence to make sure. I mean, we buy processors that says, hey, it runs at 2.4 gigahertz or it runs at 3 gigahertz, right? So that we need to make sure that across the board, we are able to satisfy the timing requirement. So that step happens, that's we call as timing and physical convergence. And finally, the formal step where the design is transported to the fabrication companies is called the tape-in. And so while this is happening, I know that I've put software as something that's after these 4 steps, but in reality, it kind of happens in parallel. So as we all understand, right? So just the hardware by itself, because of the nature of complexity, is simply unusable for the user, right? So there has to be a lot of software solutions around for the users to take advantage of it. So the firmware development, they would have very sophisticated libraries that's available, or API calls that they make available so that it's very easy for a user to implement a function on the hardware, right? I think some of you who've used Arduino boards or Raspberry Pi systems, you will understand the value of these APIs, how simple it is to make an LED blink, how simple it is to program the solution to run a servo motor, for example. So all that step is carried out by the software team, and this whole tape-in to getting the physical chip back actually takes multiple months, right? This is a very long, drawn-out process. So even though these factories run 24/7, this is a very sophisticated process leading up to like somewhere around the order of 200 to 400 steps, depending on the process. And this is a very planar process. You have to process it layer by layer. It's like making a cake that has got 200 layers. You make the first layer, you wait for some time, you do some processing, then build the next layer on top of it, and so on. So it takes months to get some of our sophisticated silicon back in hand. And that's when the silicon checkout team, take over. And their job is really to make sure that when they power on this device, things are functional, the power consumption is within the specified limits, it's able to perform, at the target values. There are no anomalies. The silicon is fairly healthy. They take a lot of measurements to get confidence on the health of the silicon, and finally they even run it through sample workloads to make sure that it satisfies the original requirements that came from the product definition phase itself. So yeah, so these are some of the typical steps that's involved, when you go through a product or a project cycle in a semiconductor space. I don't think I've included every possible sort of step here. I think there's a lot more subtle points that I couldn't capture here, but I think they should still give you a flavor for how the handoff happens from sort of one team to another, and all of these teams are part of the semiconductor industry. Okay. So moving on. So this is probably the last topic that I had in mind. So I just wanted to list a few skill sets and some kind of a job code, job description, or a job title to give you guys some information about how you can go about preparing for some of these jobs, right? So this is again, like I said, by no means a complete list, but I just put in a preliminary list for us to get talking about it, and for you to think more than anything, think about it, and if you have any questions, continue to post it on the chat, and I'll try to address them at the end of this talk. So the first set of job is the hardware design jobs. Right. So even within hardware design jobs, there's a lot of categories, right? So you have your analog designer, you have your mixed signal designer, you have your digital RTL designer, your physical design, and so on. But let's talk about what are the basic components that's involved, right? So obviously, right, CMOS, right, the complementary metal oxide semiconductor, right? So this is a foundational transistor technology which is used in all the chips that we use, right? So it's always good to understand the basics of CMOS and CMOS design. And so Verilog, which is the key hardware description language, this goes without saying, right? So I think we've definitely moved on from the days of doing a lot of custom design, which is very familiar with, I think, some of us who are just coming out of college, right? You would be able to instantiate transistors or gates in your design and create, some logic. So I'm not saying this doesn't happen anymore, but in very limited pockets. So most of the design, or 90% of the design, or even more, they've moved on to designing hardware through Verilog or other HDL languages. So make sure that that part of it is solid. I mean, there's a lot of resources online, or even free resources, I would say, to make sure that you're familiar with that. And it's always good to have, a couple of projects, whether it's a small ALU that you've designed by yourself, a simple 4 or 5 stage pipeline ALU, or CPU, a small encoder decoder kind of blocks, anything. But I think to be able to do a design from grounds up and have that experience, I think is vital to for some of these jobs, and more importantly for the interviews as well. And like I told you, there are different kinds of design jobs. So there's no one size fits all. But then if you're leaning towards digital, like I said, things like Verilog and CMOS is really important. If you're an analog, I think blocks like, phase lock low, PLL, band gap reference, voltage regulators, DLLs, memory circuits, differential amplifiers, so many, right? So low noise amplifiers. So all this are great examples and useful experiences to have when you're appearing for a sort of analog hardware design job. So System C is something which is fairly new. So I would say it's the next level of abstraction, going from gates to Verilog or hardware description language to System C. Right? It's a lot higher level. It's at a much higher level. So if you have the time, if you can spend some time reading up on System C, I think that makes a really good reading for your resume. So this is basically a library or an extension on top of C, but C usually does not understand hardware. But I think the System C is basically an extension to make the C language hardware compliant. So that's the first set of jobs around hardware design. The next set, as I told you earlier, there's plenty of jobs out there, which is with respect to the validation and verification, right? So even here, obviously, most of the designs that you validate will all be in Verilog. So knowing the language and having a mastery on the language is really important. FPGA programming is an add-on, and it'll be something that will make you as a candidate stand out. It's not essential, but it's a great technique to be able to take your design very quickly to an FPGA and run a quick test or a workload on it. The reason being is the time it takes, right? So a small audio codec example, let's say a 3-second audio codec on a simulator using Verilog might take about 24 hours to run in a simulation, whereas you run that in FPGA, it'll just take those 3 seconds because it's real time. So that's the power of being able to run your designs on an FPGA. So the next point is the OVM and UVM. So this is the open verification methodology. UVM stands for, I think, Universal Verification Methodology. So there's been a lot of thought process and framework keeping reuse in mind, and some of these methodologies or frameworks are to cater to those requirements. So again, there are a lot of information available online on some of this, but having this on your resume and also really understanding this, I think it makes you very productive very quickly when you get onto the job, right? So there are a lot of people with years of verification experience don't have the OVM and UVM, but I think as a fresher, if you can spend some time getting familiar with this, I think it'll really add value to your profile. And obviously this is not System C, this is System Verilog. So System Verilog really is an extension on top of Verilog, primarily for validation. So if you're really learning OVM or UVM, you would have covered System Verilog as part of it. And then C++ is a bonus. Again, it kind of goes without saying because the OVM and UVM are object oriented. So a lot of the concepts from C++ are borrowed for them. So by the time you are reasonably familiar with OVM and UVM, I think System Verilog and C++ is automatically there in the mix. So the third set is the algorithms. Again, there's algorithms of all kinds, and there's a lot of different jobs depending on what the company is focusing on. So for a company like Intel, there'll be a lot of focus on things like computer vision, machine learning. You look at companies like NVIDIA, they would still look at machine learning. They look at gaming, optical flow kind of algorithms, a lot of graphical algorithms. So this depends on the company, but then again, if you're very strong in sort of math and algorithms, there's a lot of opportunities in semiconductor industry, robotics, various optimization techniques, and so on. The next set is the physical design. I think we spoke about this even earlier, so I'll spend a little less time here, but the whole point is you basically take your RTL to GDS, or a format where you give it to the fabrication company. So, and there's a lot of steps like static timing analysis. I think some of you are familiar with setup time, hold time, clock frequency, drift, slew, skew. So all this comes from the static timing analysis. And like I said, there's synthesis, place and route, layout, design rule check, electrical rule check, and so many more. But this all comes under the job title for physical design. From a software point of view, there's the firmware and driver development. So this team really, spends time understanding the underlying hardware architecture and making sure that they write their routines, which is best fit for a hardware, right? So there have been times when a new feature has been introduced in hardware and the software team or the firmware team really didn't know about it, and they've never implemented that in firmware. So it's lived as a ghost feature on silicon for years together. Right, so that's why it's very important for these engineers to have a grip on the hardware architecture, so they're able to really make use of the knobs available to them. Clearly understanding of protocols that's available, whether you're talking off chip, within the die. We're familiar with things like USB, Ethernet, SATA, I2C and so on. So all of them come under protocols. C and C++ goes without saying, and then any exposure to BIOS and compilers, right? So I think that's a real bonus. So the next set of jobs is around automation. So there's a lot of manual steps that used to be in various processes in semiconductor industry, and I think over the past, let's say, 10 years or so, I think there's a lot of very smart software automation engineers who've taken it up and optimized the whole flow. So having very good handle on scripting languages and even other programming languages, I think is a must for automation engineers. There's a lot of optimization algorithms that they use, even like things like binary search, sorting, to go through a huge amount of, let's say, data to able to pick what is of relevance, whether it is to the hardware team, whether it is to the performance monitoring team, and so on. So I think a lot of that is under the scope of this area. And the last but not the least is the big set is on research. So there are a lot of engineers within every company in pockets doing research on topics which they would believe would make a very viable idea or a feature in the coming few years, right? So there are teams who work on hardware architectures, right? So we're familiar with RISC versus CISC processor, CPU architecture versus GPU, versus now TPUs they're talking about from Google for TensorFlows. So the architectures evolve over time, right? So this is the highest order magnitude knob that's available to you. You can have a lot of fancy circuit techniques, but then the return on investment that you get on tuning the hardware architecture is far greater, right? So I think there's a lot of interest and value within the company, and there's a lot of jobs as well on hardware architectures. How do you integrate? The integration is gone on to the next level in the last decade or so. So we were talking about bringing multiple small components onto one die, which is how the name integrated circuits came in the first place. And now they're really incorporating a lot of aspects of a system, and they even call it a system on chip or a system in package. So there's a lot of tight integration of a compute component with a memory component, with a communication component, with a always on sensor component, and so on. So there's a lot of importance given to how tightly can we do this integration, how efficiently we can do it. And there's a lot of optimization in terms of power and cost that comes from this. The compute itself, I think how some of the architectures, for example, floating point unit, how can they be improved? A multiplier, a divider, an exponential function. A lot of the intricate hardware blocks which eventually end up executing the function that you write in software. I think they also go through continuous optimizations. Then comes the accelerators. So these are the accelerators or hardware components that are created with one particular function in mind. Some of the phones that we have today, they can easily measure, how many steps we take or how fast we run. So these are not processed by the CPU that's present inside. If that were the case, our phone would run out of battery in a few hours. So there are specialized accelerators or chips that consume very less power and do only one thing, but one thing very well, right? So those are called accelerators. So there's a lot of scope in terms of design of these and definition of accelerators, communication protocols, a lot of emphasis on the security aspects of it. I think that's increasing day by day. There's a lot of transactions. The reasons that we use our computing resources, even our phone, I think has significantly increased over time. And a lot of us transact financially our personal information. So emphasis on security, what kind of security hooks that needs to be built in hardware so that no software hack can get around it. So those are focus of the security team. There's process teams who look at which technology node a particular chip needs to be fabricated in. A team that works on tuning operating systems, working very closely with big operating system companies like the Apples and Windows out there, or the Chrome OS, Android, etc. A lot of algorithm development in terms of computer vision, machine learning. So these are the next wave of algorithms and the next wave of devices that we're starting to see. Our 3D glasses, the AR VR systems that will make its way very quickly into either a television or entertainment system or into a video game console, or even the way you do trainings for a pilot, for medical reasons. So these are all in the making, and you will find them in the next few years a lot more accessible to everyone. The circuit design, instruction set architecture, alternate applications, and many more. Like I said, I don't think I've listed all of them, but I'm just put in a few to give you guys a flavor, right? So there's so many different areas. So if there's one particular aspect that you're interested in, my advice is to try to go deep, right? So if it's some cryptography or those algorithms or numerical methods, higher order math functions, circuits. So whatever it is, I think there is a lot of value in trying to go deep and learn what's the best work that's been done in the field, and get familiar with some of the state of the art options that's available. So I think that really makes it very compelling when you appear for an interview. A few sort of tips for the interview preparation. I think I've spoken about it earlier too. So if some of it is repetitive, I'll try to move on quickly. But from a hardware basics point of view, I think it's important to really understand. I mean, this will take you not even a day to listen to lectures like from Anant Agarwal from MIT. These lectures are really open source, and you will completely understand the basics there is to CMOS and basics of digital design. Various microprocessor architectures, and I think it's important to know how architectures evolved over time. Why did some of the changes happen? Compared to a simple CPU. Why do we have to have something specialized as GPU today? What is the difference between a RISC and a CISC instruction set or a system? Concepts like pipelining, how processors make use of pipeline to deliver very high performance. Why should you have caching or cache mechanisms in your architecture? How does that improve performance? What are the different kind of memory architectures? Some of the common chip interfaces and protocols like SPI, I2C, UART, AXI, APB. Sorry, I can't expand all these terms, but then some of the common interfaces. So these are all things that you can get familiar with when you appear for a hardware basics. And I think if you can answer some of these questions, I think you'll be a very strong candidate to get hired. And onto the languages, like I think Verilog goes without saying if you're into hardware design, and if you're more towards firmware, software, and algorithms, and C, C++, embedded C. System C, like I said, is a new sort of package or language if you look at it that way. And I think it makes your resume stand out if you can spend some time on that. And some of the usual languages like Python and Perl, MATLAB, I mean, if it's relevant to the work that you're doing. From a software basics point of view, I'm not really a software guy, so maybe this list is not complete. But again, with respect to hardware, understanding, how the BIOS works, what is the role of a compiler? How do you have to understand and translate the architecture so that the compiler can make best use of it? Basically, the instruction set architecture, the ISAs, and so on. And finally, just a few miscellaneous points. So these, I put them there primarily from my own personal experience. So we hire people time to time. So we have to sort through resumes to identify a smaller pool of students or candidates who we need to talk to. And just a few points from my experience here. So the first thing is, please don't use a generic resume. So there's many times I've noticed, even some of the top institutions in India. So we get about 50 resumes, and all 50 have the exact same template. The only thing that will be different between them is the marks they secured and their name, right? So the coursework, the project, everything is generic, right? So please don't use that because I think so it's just one resume for you, but for the person who is looking at it, it's like 50 or 100 resumes. So it's very easy for him or her to sort of dismiss the whole pile if if they see this such a generic format, nothing really stands out, nothing catches their attention. So yeah, please don't use a generic format. And try and capture details about the project and specifically the role that you did if it's a group project, right? So I think this is the most important set in the resume, right? So most of the college students or fresh graduates from college, I think this is one area that I find in the resume that's lacking. Sometimes there's a title there and nothing more to it. So I think it's really important to list, okay, what was this project about? How did you partition the various phases of this project? What was your role specifically in completing the project? I think it's really important. I think it's useful information for the employer to go through in detail and even have very relevant questions for you, and that's another advantage, right? So if there's details in your resume, a lot of times the question during the interviews will stay around those topics, right? But if there's very, very less information in the resume, then people kind of move to a generic Q&A set, and sometimes it might work to your favor and most of the times it might not. So I think it's really important to take time to write about your resume and spend a little time fine-tuning the resume before sending it out to a particular job or a company for a particular job requirement. And I think that's something that can help your resume again stand out. It almost seems like you're almost talking in a one-on-one way with the employer, saying that, okay, this was your requirement and here's my resume, which kind of checks for most of the requirements that you have. So spend some time, fine-tuning. It's a bit of an effort, but I think it's really worth it if you could do it. Things like personal details on hobbies and extracurricular activities don't matter. So yeah, I think it's name, your contact details, I think is more than sufficient. Anything beyond that, I think nobody really looks at it anymore, at least. And try to have a few conferences, publications that you constantly read or you're a member of, right? Like an IEEE, for example, right? And there's so many more. There's CVPR for computer vision, there's ICRA, for robotics, and there's so many such conferences and publications. So try and, get into the habit of just being plugged into any one of them. And I think a lot of them have student membership, which is either free or really, really reasonable, so that you are, again, familiar with some of the topics that is going around in the research world. And if you have some link to that in your resume, some mention of that in your resume, that really adds value, right? And like I said, take time to craft your resume, right? So don't try to get done with it quickly. I think this is your window to the employer, and I think any extra time that you spend in doing that, I think it's time well spent. So yeah, be succinct, be crisp, and really be original, right? So okay, so I think I've actually taken longer than I expected. I think I've used up about 15 minutes. So I'll quickly go to the live chat window and see if there's any questions, and I'll try and answer them. Okay, so there is a question from someone called Jack Sparrow about how to improve our RTL programs in practical manner. Because we studied about it theoretically and don't know and how to implement this too, right? Yeah. So yeah, good question. So the only way to do this is actually start writing, these programs, and there are a lot of forums out there for VLSI where you can actually post your RTL programs, whether it could be state machine design. Or your memory subsystem design, or any protocol or any logic that you've implemented. So I think if you spend some time describing what your problem statement is, your flowchart that you followed to implement this design, and finally the code itself, and you post, I think there's a lot of people who would take time to study this and reply, and a lot of teachers and lecturers or people with experience part of those VLSI forums. I think that could be one good way for you to get some feedback about your design, right? But yeah, writing it yourself and simulating it will tell you a lot, but then posting it on some forums and having more eyes look at it, I think, is a way to improve your design, the quality of your design. Okay. Okay, so okay, there was another question from Sailitika Potluri. And what is the full form of OEM? So OEM means original equipment manufacturers. Yeah, sorry, I didn't put the full form there. So these are, like I said, the companies like Apple and Dell, HP. Uh, some of these Samsung, you buy the devices from in shops, right? Whether it's a cell phone or a tablet, or a laptop. So the guys who finally sell the end product to the user, they are called OEMs, the original equipment manufacturers. And a lot of semiconductor companies, again like Intel and AMD or Nvidia, they sell their solutions to the OEM companies, who then integrate it as part of their platform and provide it to the user as a product. Yeah, so thanks for the question. The next question is Harish about how to get hired by Intel India. So Harish, I think what I would suggest to you is go to jobs.intel.com. I mean, there's a very detailed posting for every job that you'll find. I mean, some of us, when we post our job requirements, we take time to write it up. You'll find a lot of lines of description of what is expected for a person who's trying to take up this job, or what is expected of them in terms of what they should know coming to the interview. So I think there's enough information there, and this is true for even other companies. So take time to go to the company's website and see. I know that we are all used to going to websites like LinkedIn and other job aggregators, but I think there's a lot of value in spending and going to the company websites, because a lot of time those requirements are not posted on these other common portals, right? So I think you should make a list of the companies that you're interested in, and time to time go and check jobs.company.com, and I think probably that's the best way to go about it. Okay. Sai Litika Potluri, is accent important in interview to get selected? No, definitely not. No, it's not at all important. So I think what matters is the grasp that you have on the subject matter and how you're able to answer. And so a lot of times in interviews, I think you can even tell the interviewer upfront that I have a slight sort of language problem, so be slow with the questions, or I'm going to be slow with the answers. Is it okay? And I think people are totally fine. And even if I look at my own team, I think there are people who can communicate very clearly, and then there are some who probably don't have that strength when they started out. But it doesn't mean that they are any less successful. So I don't think it's very important to get hired. Do Intel or Qualcomm hire people with bachelor's degree? This question is from Santosh. Yes, they do. Right. So even in my own group, I've hired people with bachelor's. So that's definitely a possibility. Some of the jobs will call for a master's, but like I said, if you spend time looking through the job requirements, and if you feel that so for some of the tools or the techniques or some of the job requirements, somehow you're confident based on your own projects and experience, I think you can hire, even though they ask for masters, and clearly say that I do feel that I have some of the skill sets, and that's why I'm going ahead and applying. So you can even drop that line as part of your covering letter. I think a lot of managers or interviewers really appreciate people looking through the job requirement in detail and taking a call for themselves, or taking a stand for themselves, and being confident about it. So clearly, I think they will hire with bachelor's degree. And one more tip for folks with bachelor's degree is keep checking for internship opportunities. So a lot of times the time it takes for a master's student to get productive in the company to a bachelor student is somewhat different, clearly because of the additional exposure that the master's candidate would have with respect to time in the lab, tools, and so on. So if there is internship opportunities, the companies are generally very flexible about what they expect from interns, and they'll give you time. More importantly, they'll give you time to ramp up, right? So a lot of things you can get to the company, take your time to ramp up and be productive. And anytime the employer feels, the group feels that you are going to be an asset to the group, they at that point they'll forget about degrees. It does not matter whether you have a bachelor's or PhD. They will, try and pick you up. So yeah, prepare well, and then keep looking for the intern opportunities. Okay. Harish is asking what chip is used in mobiles. So there are many chips, Harish. So some of the popular ones come from obviously companies like Qualcomm. They have their own chips. Apple, makes their own chips. There are solutions, atom-based or core-based solutions from Intel. Many companies. There's a lot of solutions out there. And I don't think there's any one chip. And in fact, Intel's chips are like a de facto standard for the server grade or the server computers or even desktop clients that we're all using. Maybe even to a certain extent on tablets, but I think on mobile phones is one area that Intel is still work in progress. They're really trying to crack that market. Yeah, but it's a difficult one, and companies like Qualcomm have a head start, and Samsung have a head start there. Again, I think Vashini has asked the same question about bachelor's or master's. Like I said, there will be more opportunities if you have master's, but it's not to say that with bachelor's you can't get it. And just make sure that, and this is something you can validate it for yourself. If you spend some time understanding the job requirement, and if you're able to tell yourself that I seem to be knowing most of this stuff, I think that should not stop you anymore. I think Raj has a question about what are the basic requirements from our side to hire semiconductor industries. Yeah, so I think so. A lot of the stuff that I went over in today's talk, Raj, I think kind of covers that. Whether it is sharpening your technical skill sets in a particular domain, and there are a lot of domains, and being able to have some experience, getting your hands dirty, whether it is coding in Verilog and simulating, whether it's designing a circuit, whether it is writing a piece of code for a particular library, So I think, like I said, I think in one word, if I were to say that, I think relevant project experience is what I would say is basic requirements from your side that you can do. I think Sirisha has a question about OVM and UVM. So, like I said, it stands for Open Verification Methodology and Universal Verification Methodology. So, a lot of companies, like for example, like Synopsys and many other companies, are part of this standards sort of committee. So they came together and said, look, if it's so difficult for us to, go from one company to another or one product to another within the company because the verification methodologies are different, and we are unable to reuse many things. And this is one thing that I think we are behind compared to the software world, where a lot of the code there is very modular, easy to reuse. But in hardware industry, I think till about 10 years back, nobody was talking about reuse. Everybody was doing their own thing. So if you went from one group to another or one company to another, you would actually be not at all productive for the first few months. So I think that's when I think people came together and said, you know what, maybe this is not good for the industry as a whole. Let's come up with a methodology. So this is basically, I don't know, you can think of it as a methodology or a library or a framework where there is a lot of functions available to you. So once you understand this, you can reuse a lot of functions available in the system to verify your module, right? So, and let me give you a simple example, right? So let's say you design a small traffic signal, sort of a module, and you give an USB interface so for people to program saying that okay, right now, red light, I want the red light to come on, or yellow, or the green, right? So I know USB is very simple for us because we just plug and play, but it is one of the most complicated interfaces in terms of programming it, right? So if you were to program as part of your testing, some sequences through this USB so that you can get the command in your traffic generator module to display this colored light, you will spend 100 times more effort in designing this interface or this module that can communicate to UVM through the USB versus designing your own traffic generator module. So clearly that's not efficient, right? So the OVM and UVM gives you modules, gives you methods and functions where you can say, okay, you know what, I want this USB sequencer or driver, and you can go and program in 2-3 lines saying that, okay, please send this data packet, and it will send it. So it's basically a framework that helps you to reuse a lot of aspects of verification. So this OVM UVM is a multi-day training that happens in a lot of companies. So I don't think I'll be able to do justice here, but that's in sort of 1-2 minute answer to your question. Harish wanted the contact details. Sure, I'll drop it with the SixPhrase team. I think you can get in touch with them, and then yeah, sure. I mean, if you have any queries, feel free to send it. I think Ravi has a question about the most useful chip. Like I said, I think there isn't a single useful chip. It depends. It depends on the application. So the Xeon chips from Intel are probably the most useful when it comes to servers. So, for example, the very YouTube feed that you're watching comes from YouTube servers, which will be powered. I mean, I'm 99% sure it's powered by an Intel Xeon processor. So that's really useful for all these server grade, cloud applications. And when it comes to desktops and mobile, I mean desktop, laptops, a lot of the core processors from Intel, like the Core i5, the Core i7 are, I think, some of the de facto standards. And for when it comes to mobile, I think there's a lot more diversification there. And like I said, companies like Apple have their own solutions. Samsung does too. There's very good solutions from MediaTek, from Qualcomm as well. So yeah, so it depends on the application itself. Yeah, I think Jack has this question about interview expectations for resume. So like I said, I think that's probably what I covered. Be honest in terms of what you know, and keep it as technical as possible. Spend a lot of time writing about the details of your project, and not necessarily explaining the problem in detail, but explaining your role and what you accomplished for that particular project in detail. I think that's probably I think what I would expect. And be original. Don't try to take templatized resumes. I think it makes a lot of difference when if someone's going through like 50, 100 resumes. When there is a resume that looks different, your eyes automatically goes towards it. You give it a little bit more attention. So yeah, be original. I think that's my advice. This question from Dinesh about opportunities for ECE students in India. And how computer science and EEE students can also be having opportunities in the core companies. Yeah. So like I said, I think there's even for a group like or a company like Intel, I think there's a lot of people from EEE computer science and ECE that get hired. So there are different jobs that I went through, right? So there are some really hardware core design jobs, which you will obviously find a lot of ECE students in. But there are a lot of EEE students too. There are a lot of power amplifiers and power delivery circuits, switching amplifiers that are designed, voltage regulators. So a lot of power electronics concept, which is taught quite well in EEE. They are utilized for those jobs. So yeah, and there's healthy overlap of electronics in EEE as well. So I don't think there's a huge differentiation between ECE and EEE within the company, to be quite frank. And this is lots and lots of jobs for computer science students. It can be firmware jobs, operating systems, automation, IT jobs within the company. There's a lot of infrastructure that's available. So I think, like I said, I think there's more computer science jobs even within Intel than EC and EEE, but then there's jobs for all of them. Um, I think Raghavendra has questions about physical design. Yeah, like physical. Yeah, so physical design and verification validation are probably the two most job. I mean, are the two job codes that have the most opportunities, right? So, and for some reason, I think the fresh college students who get into Intel, I find them very productive in both these areas, right? Whether it's physical design or validation. So yeah, there's plenty of jobs, not just within Intel. I think the whole industry. I think these two are the jobs are the job categories where there's a lot of options. You can go from one company to another and still be very relevant from day one. Now, I'm not asking you to jump jobs easily, but it's something that you can easily do if you need to. Okay, so Dinesh has another question about how they can add value as a fresher by undergoing few certification courses. I think that's a great question. So what I can do is I might not be able to tell everything right now on top of my head. I can send this a compiled list to Dinesh offline, and he can share it with with the rest of you as well. But like I said, for Verilog, there are courses offered by companies called as Sutherland. And these are charged courses, but I think it's a 3 or a 4 or 5 day course. It's worth the investment, right? So if I had known such a course existed during my bachelor days, I would have spent the money and taken up this course. They have live sort of web-based courses. They will teach you the concepts. They'll give you time to do lab exercises. At the end of this 4 or 5 days, you will be a very seasoned RTL design, person. And there are a lot of jobs out there for RTL design engineers. And if you have this certification on your resume, and I'm sure you'll be able to crack the interviews as well with respect to RTL. So yes, there are courses for design. There are courses for UVM and OVM. There are courses for physical design tools like place and route, synthesis tools. So a lot of these sort of bread and butter jobs have very good tools out there. Some of them are free on YouTube, but some of the paid courses will force you to take up the lab exercises, and you'll be, you'll find yourself a cut above once you finish the training. So I can send that list to Dinesh, offline, if that's going to help all of you. And I think Dinesh says the last question is, how will the job opportunities and challenges for circuit branch students after the COVID-19? Yeah. So, I don't think I'll be too worried, about COVID, because I think one thing that we're all noticing, even being within the industry and the company, is the demand for a lot of these compute platforms and solutions that the hardware companies manufacture seem to have gone up during this time, right? So a lot of schools, for example, that never even thought about going online are forced to go online, right? And the ratio, one golden sort of rule that I've learned is, for every 4 people who use the smartphone to access an online service, be it YouTube, or any other streaming service or platform, Intel sells one new server to the company, right? One new server, which means a lot of memory is sold, a lot of memory chips, and the whole ecosystem, which is why we spoke about the entire chain, right? So I think, especially during this COVID time, I think when a lot of solutions are going more and more online, people are transacting financially online, they're sharing, education is going online, the way the business is being conducted, a lot of them, whatever is possible is being taken online. So I don't think you have to worry a lot in the long term about how this COVID would change the face of the semiconductor industry. Maybe for a really short time, generally companies go through a hiring freeze, right? Whenever there is a news of a recession or a financial crisis, companies just take it a little conservatively and say, you know what, next 3 months or next 6 months or 4 months, let's not hire people, just to keep things in check. So yeah, so in a very short term, you might face this, but I mean, again, if I were you, I would take it very positively. Maybe it's a blessing in disguise for you to spend the time needed to sharpen your skills, go through some of these courses. Because I think coming from
pretty decent engineering school in Tamil Nadu, I can tell you that a lot of the things I learned in college was not directly relevant for me on the job, right? So I think if you had some time to yourself, there's a whole lot of resources available, whether it is in MIT or Berkeley or Stanford. A lot of these top schools that most of us didn't get an opportunity to go to, but their coursework is available for free, right? So tell yourself, okay, here are the three courses I'm going to do. Some digital logic and analog system design, and Verilog, for example, or some embedded course, or anything that interests you. Just give yourself 2-3 courses, and spend the next 3-4 months if you have that to finish some of these courses. And I think you'll be a lot confident about yourself. You will definitely be in a better position to crack the interviews when they open up, and you will certainly be a very good employee when you get on board. Okay. Um, yeah, I think Harish asked this question about the name of courses. Sure. So I think I'll write to Dinesh, who's part of the SixPhrase, with a list of sort of courses that you can take. With some of them are free, some of them could be paid, but then you can make the choice. Yes, I think Sirisha has certification question about certification courses. Uh, are there online? Sure, I think there are, especially on Verilog. So the analog is slightly difficult because there's no quick, a 5-day course that you can go from 0 to 100 in analog design. So that you need to take the courses that are available in universities, like top universities like Purdue, Stanford, Berkeley, and so on. So that needs a few months of investment, but there are questions. I mean, there are courses, and you can get certification, and there's academy like Udemy, and you can pay for a very, very nominal fee. You can get the certification from them once you complete the course and turn in your assignments. So yes, it's definitely possible even in hardware. I think Yamini has a question again on the courses. Oh, sure, I'll write to Dinesh, and hopefully he can share this, with everyone who attended the seminar. So it's something that you can look up. Okay, so that's probably all the questions that came. Any other questions before we wrap up the session? Okay, so I just want to thank all of you again. I think you've given, I think, 1.5 hours of your Sunday for this talk. So thank you so much. I hope it was useful to you in some way. I mean, I was really excited to bring this talk to you. I just put myself in your shoes not too long ago. Having a lot of the questions that you have. So I hope it was of some use to you. So thanks, and good luck to everyone. Yep. Thanks. Bye.